This is section 12.1, Estimating Limits Graphically. Estimate limits at a point. Calculus centers around two fundamental problems. One is finding the equation of a line tangent to the graph of a function at a point. Let's see what that looks like. If we have a graph, let's say a parabola, and we have what's called a tangent line to the curve, that means the line touches the curve at one spot. In calculus, we like to know what the equation of that line is at the given point. And then finding the area between the graph of a function and the x-axis. Let's say we have a parabola also, and we want to try to find the area under the curve, between the curve and the x-axis, from let's say 2 to 4. We would like to know what that area is right there. Fundamental to the solutions of each of these problems is an understanding of the concept of a limit. So what's basic to both of those problems is this concept called a limit. Recall from lesson 1.3 that if f of x approaches a unique value L as x approaches c from either side, then the limit of f of x as x approaches c is L. Written, the limit as x approaches c of f of x is equal to L. In other words, let's say we have this c, an x value. Let's say it's 5, and the y value is 10. If we approach 5 from the right, the limit or the value is 10. If we approach 5 from the left, in other words, approaching 5 from the left, the function is approaching 10 from the left as well. If this happens, if both one-sided limits approach the same value, then the limit is, in this case, 10. You can apply this description to estimate the limit of a function, f of x, as x approaches a fixed value c, or limit as x approaches c of f of x, by using a graph or making a table of values. Estimate a limit equal to f of c. Estimate limit as x approaches 2 of negative 3x plus 1 using a graph, and then support your conjecture using a table of values. Let's turn on our calculator. Go to y equals, and we have negative 3x plus 1. And if we look at a graph, there's the line, the negative 3x plus 1, and we're looking at 2. So if we go to calculate, and we're going to calculate a value, we want to calculate that value when we plug 2 into the equation. And it turns out that the answer is negative 5. So the limit as x approaches 2 of f of x, of the function we're looking at, is equal to negative 5. Now if we want to look at this a little closer with tables, so we've used the graph, we want to look at tables, then let's plug in values that are really close to 2. Let's plug in 1.99, and we can do that with our graph. We can go value and just go 1.99, and it's equal to 4.97. So here's the x value, here's the y value. It's negative 4.97. How about 1.999? That just, if that says negative 5, then we'll go back to the home screen. 1.999. Press enter, and it's negative 4.997. Now that's approaching 2 from the left. What about 2 from the right? What about 2.01? 2.01. That is equal to negative 5.03. And then if we plug in 2.001, then we get negative 5.003. If we go from the right, if we're getting closer to the right, we're getting closer to negative 5. And as we approach 2 from the left, we're getting closer to negative 5. So just by the table, we're pretty convinced that the answer is finally negative 5. So I've used a graph and I've used a table. Estimate a limit. Estimate limit as x approaches 3 of x squared minus 9 over x minus 3 using a graph. Support your conjecture using a table of values. Let's go to y equals, and the top is x squared minus 9. And then we'll divide that by x minus 3. We hit graph. There's part of the graph. Actually, it's a line. And we are finding the limit as x approaches 3. So we go to Value, Calculate, just press Enter on number 1, and we're looking at 3. And notice it is blank. And it's blank at 3. Let's go over to 3, and we're actually up here somewhere. Well, now I'm not sure what the limit is, but I could use a graph to just maybe kind of estimate it. And but let's use a table. X, Y, and we can't plug in 3, but we can plug in something close to 3. How about on the left-hand side? 2.99. Roughly 5.99. So 2.99 gives us 5.99. How about 2.999? That gives us 2.999 gives us 5.999. Now if we go, that's on the left-hand side. If we go on the right-hand side, that'd be 3.01 is equal to about 3.01 is equal to about 6.01. And then if we plug in, how about 3.001? 3.001, we get 6.001. Looking at the left-hand limit and the right-hand limit, I'm pretty confident that the limit of this entire thing is 6. So the limit as x approaches 3 of the function f of x is equal to 6. Independence of limit from function value at a point. The limit of a function f of x as x approaches c does not depend on the value of the function at point c. What that is saying is, notice right here at c there is no function value. F of c does not exist on this one. There's no point here. But the limit is still defined because the limit, the left-hand limit and the right-hand limit are equal to each other. Let's say this value was x value of 5 and this was a y value of 10. The limit as x approaches 5 of this function, whatever it is 10, even though there's no point exactly at 5. The same with this. If this is 5 and this was 10, the limit as x approaches 5 would be 10, and if this up here was 12, the point, the limit is not 12. F of 5 would be 12, but the limit would be equal to 10 if we give this some values. Now on this one, notice that the value of the function f of, if I gave this 5, f of 5 is 10. Not only that is 10, but the left-hand limit and the right-hand limit are also 10. So the limit as x approaches 5 of f of x is equal to 10. And that is the definition of being continuous at a point, or the definition of continuity. If your limit and your function value equal each other, then that hole is filled in and the function is continuous at that point. In finding limits using a table or graph, we have looked at the value of f of x as x approaches c from each side. We can describe the behavior of a graph from the left and right of x more concisely in terms of one-sided limits. We have the chart here, one-sided limits. Left-hand limit. If the value of f of x approaches a unique number L as x approaches c from the left, then the limit as x approaches c from the left, there's a little minus sign there, of f of x is equal to L1, which is read, the limit of f of x as x approaches c from the left is L1. And then we have the same thing with the right-handed limit, except we have a plus here above the c instead of a minus. Using these definitions, we can state more concisely what it means for a two-sided limit to exist. Existence of a limit at a point. The limit of a function f of x as x approaches c exists if and only if both one-sided limit exists and are equal. That is, if the left-handed limit is equal to the right-handed limit, then there's a limit at that point. Estimate one-sided and two-sided limits. Estimate each one-sided or two-sided limits if it exists. A. The limit as x approaches 0 from the left of the function, from the right of the function, and then state, is there a limit at 0? Let's look at the graph. Y equals, let's clear this, and we need absolute value of 2x. That's under math, and I believe it's under num. absolute value of 2x, and then we're going to divide that by x, and we will look at the graph. Interesting graph. We have a line to the left of 0, we have a horizontal line to the right of 0, and we're looking at what about at 0. Let's look at the left-sided limit, and we can do that by plugging in something very close to 0 from the left. How about negative 0.001? It would appear as if the left-handed limit is negative 2. So the limit as x approaches 0 from the left of the function is equal to negative 2. Let's look at the right-handed limit. Limit as x approaches 0 from the right of the function. And we can plug in a value very close to 0 but on the right side. So how about positive 0.001? This value is a positive 2. So 2. Now since the left-handed limit is negative 2 and the right-handed limit is positive 2, then we can say the limit as x approaches 0 in general of f of x does not exist. Let's find the limit on this one as x approaches 1 from the left, 1 from the right, and then let's find out what the limit is at 1. Let's draw these by hand since it's a piecewise function. We have x to the third plus 2. Well, x to the third looks something like this, and then we push that up 2 units. So 2 units, but we're only graphing to the left side of 1. So if I plug 1 in, I get 3. 1, 2, 3. And then it's going to look like something like that. And I actually want this dot, now that I look at it, to be open because it's not equal on this one. And then I have the line 2x plus 1. If I plug 1 into this one, I get 2 plus 1 is also 3. And then I have a slope of 2. So then rise over run, and then I have a slope of 2. The limit as x approaches 1 from the left of f of x is equal to 3. And the limit as x approaches 1 from the right of f of x is equal to 3 as well. They both approach 3 from both sides. So then we can say that the limit as x approaches 1, just in general of f of x, is equal to 3. If this line would have been up here, let's say, same line, but same slope, but pushed up 1, then this piece would not come in contact with the other piece. And we would have a left-sided limit would be 3, the right-sided limit would be 5, and then the limit at 1 would not exist. Limits and unbounded behavior. Estimate each limit if it exists. The limit as x approaches 4 of 1 over x minus 4 squared. Let's plug that in. Let's take a look at what the graph looks like. 1 divided by x minus 4 squared. And we'll graph, and we'll look where x is equal to 4. Now this is unbounded. This is to the left, the limit is shooting up to infinity, and from the right it's shooting up to infinity. Let's figure that out with a table. If we calculate a value, and let's do the limit as x approaches 4 from the left side of f of x. And we'll do that by plugging in something very close to 4 on the left-hand side. So how about 3.999? And that's equal to, let's see, 1, 2, 3, 4, 5, looks like 1 million when we plug in 3.999. So that's shooting off to infinity. Then the limit as x approaches 4 from the right of f of x, how about something very close to 4 but on the right? 4.001. That is off to 1 million as well, which means the closer we get to 4, the more the higher the value is going to get. And we actually have a vertical asymptote here because 4 is what makes the denominator 0. Now this got a little messed up, but this says the limit as x approaches 0 of 1 over x. Let's plug that into the calculator. 1 divided by x. and we graph. Now the left-handed limit is going down to negative infinity. So we say the limit as x approaches 0 from the left of the function is negative infinity, and the limit as x approaches 0 from the right of f of x is positive infinity. As we approach 0 from the left, or excuse me, from the right, we're going up to positive infinity. So the limit as x approaches 0 of 1 over x does not exist. A limit can also fail to exist if, instead of approaching a fixed value, f of x oscillates or bounces back and forth between two values. Let's graph cosine of 1 over x. And we'll look at the graph. When we are zoomed out, everything appears to be somewhat normal when it dips down, but let's zoom in. Let's go zoom. One of my favorites is Zoom Box. I have lots of control with Zoom Box, and let's kind of box in the interesting area, which is around 0. Whoops, I kind of drag that. Press enter on the corner, and then we'll press enter on the other corner, the opposite corner. And notice how as we get closer and closer to 0, this function is oscillating to 0. And it kind of oscillates the other way also. If we zoom in again, use Zoom Box, we will continue to see this oscillation. Yeah, let's go even closer to 0. There it goes up and down, and it will continue to do that forever. Now if we try to plug the value 0 in, notice that the y value is actually blank. Now this function will continue to oscillate forever as it approaches 0, and it will never get to 0 on both sides. So we say that the limit as x approaches 0 of cosine of 1 over x does not exist. Y limits at a point do not exist. The limit of f of x as x approaches c does not exist if f of x approaches a different value from the left of c than from the right. F of x increases or decreases without bound from left and or right of c. So this means that right and left are different, and this would be infinite. So it's going to infinity on one side and maybe negative infinity on the other side, or even if it goes to infinity on either side, then we say there's no limit. Or if f of x oscillates between two fixed values, like we saw before. Estimate each limit if it exists. So how about the limit as x approaches infinity of 1 over x? Let's look at 1 over x. 1 divided by x. Let's clear this. 1 divided by x. And we'll graph 1 over x. And I am very zoomed in, so let's change that. If we go zoom number 6, that's the standard window. And notice that as x approaches infinity, 1 over x is leveling out to 0. So this is equal to 0. Now, going to infinity is the same as your ending behavior rules. And when we graphed rational functions, if we had something like 3x squared over 2x to the third, if the lower exponent was bigger, then this was an automatic 0. And we actually have it in this case. We have x to the 0, that's 1, over x to the 1. So the bigger exponent is in the denominator, so that's an automatic 0. With our ending behavior, in other words, as limit as x approaches infinity, if the bigger power was in the numerator, such as this, maybe, then this is shooting off to infinity. So in other words, we would say no limit in this case. And then if the function was tied with the exponents, let's say 2x squared over 3x squared, then the limit would be 2/3. It would be the coefficient. Let's look at this one. We have negative 3 divided by x squared, and then plus 2. Let's look at this graph. This one is leveling off. But let's see if we can find out why it's leveling off. If we do the limit of this piece right here, well, let's see where it's leveling off. Let's go calculate, and I think the biggest value we can put into this is 10 because our window stops at 10. But it seems to be leveling off maybe to 1.97. I'm sure if I put bigger values in, this would be closer and closer to 2. So this is actually 2. And the reason is this piece right here, if we take the limit of just this piece, this is equal to 0, and the limit of just 2, well, think about the function 2. 1, 2. It's a horizontal line. And the limit of this one, as x approaches infinity, is just going to be 2. So this piece is 2, therefore the entire limit is 2. The limit as x approaches negative infinity of e to the x sine of 3 pi x. Let's take a look at that function. We need e to the x and then times the sine of 3 pi x. Is that right? E to the x sine 3 pi x looks good. Let's graph this one. It's really hard to see, but as the limit as x approaches in negative infinity, the graph is oscillating and approaching 0. We can see that if we change our window and just go from -1 to 1 on the y-max, graph that, you'll see off to the left that is actually approaching 0. It's getting smaller and smaller and smaller. And then as we go to the right, as x approaches infinity, the values are just getting bigger and bigger and bigger. So the limit as x approaches negative infinity of f of x, that's equal to 0. And the limit as x approaches positive infinity of f of x does not exist because the values are just getting bigger and bigger as we go to the right.